Okay, now let's see work with the example. So steam is the working fluid of an ideal Rankine cycle with superheat and reheat. So you have superheat and the reheat both, right? Steam enters the first stage turbine at 8 megapascal and 450 Celsius and expand to 0.8 megapascal. It is then reheated, so it is reheated to 100 Celsius before entering the second stage turbine, where it expands to the condenser pressure of 0.04 megapascal. The net power output is 100 megawatt. Determine the part A, the thermal efficiency of the cycle, part B, the mass flow rate of the steam in kilograms per hour, part C, the rate of the heat transfer Q from the condensing steam as it passes throughout the condenser in megawatt, and discuss the effect of reheat on the vapor power cycles. Right? So let's see, mark these things in the sheet, right? So so I have to the PDF, right? Okay. Right. So this is how the TS diagram look like, right? So we start from number 1. So this the 1 to 2 is pump action. We have isentropic compression 1 to 2. Then we have the heat addition in the boiler 2 to 3. So the 2 to 3 the heat addition in the boiler, constant pressure heat addition at 8 megapascal pressure. Then 3 to 4 we have first set of turbine. First set turbine, this is a high pressure turbine. So expansion, isentropic expansion through the high pressure turbine. Then 4 to 5 is the reheat, right? So 4 to 5 reheat in the boiler, heat addition again. Then 5 to 6 isentropic expansion in the low pressure turbine, right? If you mark these things values, so we have in here the 8 megapascal line, constant pressure line. This goes like this, right? Then we have the intermediate pressure 0.8 megapascal line like this, and then the low pressure line 0.04 megapascal, right? And also it is given as entry point for the high pressure turbine temperature is 500. Now this is wrong, right? This should be wrong. This is wrong, right? This one is wrong. Okay, this part is wrong, and right. So this should be 500, and here the number 3, it should be 500, right? Okay. Let me try to okay. Now in here should be 500. Okay. Right. Right. So so this is what the question provide. P3, we know P3 is 0.8 megapascal, and temperature is 500 Celsius, and also we know the pressure at 0.4 is 0.8 megapascal, and also we know pressure at 0.5 should be 0.04 and 400 Celsius, right? So so these values are given in the question. So what the first section is, section A is to calculate the efficiency, right? So if you look on that one, so yes, 400 Celsius and 0.4. Part A is the thermal efficiency of the cycle. Now if we formulate the equation for the efficiency, so neta should be the W net, the network output divided by the Q in, right? So so we can formulate W net and Q in like this. Now let me come back here and check. So we have workout 3 to 4, we get the workout, and also 5 to 6 also workout. So we have first set of turbine, that's mean high pressure turbine, we get a portion of the workout, and also low pressure turbine also gives you some part of the work out, right? Then 1 to 2 is the pump action, where we so that we give work in. So this is work in, this work in, and this work out. 3 to 4 and 5 to 6 work out. 1 to 3 2 is work in, right? So therefore we can formulate the equation like this, right? Work out plus work in minus, right? Therefore we can define H3 minus H4. This is basically the high pressure turbine action, and H5 minus H6 again low pressure turbine action, and minus because work is in the work in is minus in the pump, therefore minus H2 minus H1, this is the pump work, right? So turbine work, high pressure turbine work, low pressure turbine work, and the pump in, right? So minus pump in. So this is the W net, and the next thing we need is Q in. So we have two set of part where we add heat. So 2 to 3 is one set, one part where we adding heat, and the 4 to 5 again the reheat, where we add the heat to steam. So with that we can define Q in as H3 minus H2 and H5 minus H4, right? So if we able to find out all these enthalpy values, then we will be able to define the neta value, right? So that's the plan for this question. So basically find out all these H1, H2, H3, H4, H5 and H6. If we be able to find all these enthalpy values, then we will be able to find the neta value, right? So let's we start from number 3, right? Because number 3 we have it's already given some parameters in the question itself, so therefore we can start from H3, right? So we know the pressure and we know the temperature, therefore we can refer, and we know it is in the superheated region, right? So number 3 and number 5 surely should be in the superheated region, but we don't know about the number 4 and number 6, whether it can be in the superheated region or else it can be in the saturated region as well. So we will find out where it is, either in superheated or saturated region while we go through the example. But first we start with number 3. So we know P3 and T3, what we need to find is H3, right? Enthalpy at the point number 3. So for that we can refer superheated tables, right? We know pressure and temperature, so we can refer the superheated table, right? If we go through the superheated table, right? So we have superheated water A6, right? We go to A6, right? Okay, now what we are interesting is the pressure is 8 megapascal. So if we go to the pressure 8 megapascal, right? So we have the 8 megapascal table in here, and the interesting temperature is 500, right? So 500 all the way up to here. So these are the value, enthalpy value. This enthalpy value 3399.5 is the enthalpy value, and 6.7266 is the entropy values, right? So we can copy those values, example, right? So from the table we can get H3, right, from the table, and S3 equal to S4. Now if you look on this, because this isentropic expansion, right, isentropic expansion, so during an isentropic expansion, you know the entropy is constant, right? Therefore S3 equal to S4, right? Therefore we can find the same thing in the table, S3 equal to S4, which is equal to 6.7266, right? Then right, so we have, okay, then we know the H3. Now the next thing is we need to find the H4. So the problem is, where is that point will be? Either it can be in the superheated region or it can be in the saturated region as well. So to find out that one, so we can refer the saturated table, right? Saturated table, and consider this pressure line, right? 0.8 megapascal line, and find out the S value in here. Now you have SLE here, right? That means entropy in the liquid. So now you have 100% liquid here and 100% gas here, right? So in this point, so you can find the SG value here, right, and compare with the S4 value. Then we can find out whether this point lies in the superheated region or the saturated region, right? Now if we go back to the saturated tables, right? So we are interested in find out the 0.8, right? 0.8 megapascal. That's mean 0.8 mean 800 kilopascal. Now this, if you look on these things, saturated SG is 6.6616, right? So this is the value, 6.6616, right? 0.8 megapascal SG, right? 6.6616. Now if we compare that one with the value that we get in the last, now we get S4, right? So S4 is 6.72, and we get our saturated value is 6.66. that means so this is 6.66 and this is 6.7, right? That's been number 4 is in the superheated region, right? So so that is what is given in here, right? Let me zoom out a little bit, right? Okay, so we know from the table, saturated vapor entropy SG at 0.8 megapascal is 6.6616. Therefore we can consider 0.4 is in the superheated region, right? Then right, so the next thing is calculating the H4 values. So first of all, we need to find out what is the fraction, right? So so we can get that fraction. Let's say the fraction is x using the entropy values. So the saturated value is this 6.6616, and this value 6.8177 is the value in between, right? So if we go back to the superheated region, superheated tables, right? So in superheated region we are interested in checking 0.8 megapascal, right? So this is 0.8 megapascal. Why? Because so this line is 0.8, right? So this is the one we are considering, right? So we need to find H4, and the pressure is 0.8 and it is in the superheated region, right? Therefore we consider superheated tables, right? Superheated table, and pressure is 0.8, right? So the saturated value is given S values as so we get this one from saturated table as well. So the same thing is given in here, 6.6616, and the next one at 200 Celsius we have 6.8177, right? So we are extracting these two values, right? 6.6616 and 6.8177. Then we can formulate the fraction, right? So, okay, that is right here. So these are the two values we get from these superheated tables, right? And this one, the value we need is in here, right? The value we get for the S4 is 6.7266. So with that we can formulate this equation for the fraction x4. Let's say it is x4, and x4 is 0.6085. Right? So with that then we can calculate the h4 values. Right? So again, this value is from the superheated table, right? And the fraction time the difference, right? Now we have these values. 2768 is from the superheated table. If we go back to superheated table, right? So these are the values: 2768.3 plus x time this difference, right? X time 2839.8 minus 2768.3, right? That is what is in here. Okay. So that is what is given in here, right? So with that you can calculate the h4 value, right? Where's the h4 value? Okay. h4 value. Right, so I think I forget to calculate the h4 value. Right now you need to calculate this one, right? So instead of calculating, I may get h4 equal to 2768.3, but instead h4 should be 11.8 kilojoule per kilogram, right? So you have to take h4 value as 2811.8, right? So we have so far we have found out the h3 and h4. So the next thing is h5 value, right? So so in the table, so h3 is okay, h4 is okay, then h5. So h5 also we can easily find using the table, because pressure and temperature is given, therefore, and it is in the superheated region, right? Therefore we can refer the table to superheated tables to get the h5 values. So if we go back to the superheated table, so we are considering the P pressure is 0.8 and the temperature is 400. Right now it's heating. After going to the boiler, the steam is heated up, therefore the temperature is 400, and the 400 here, and this is the value, entropy value, sorry, enthalpy value we are interested in, and entropy is the 7.5735. so enthalpy is 326.7.7, right? We come back to here, this is what we get, enthalpy h5 and s5 entropy can be extracted from the table, and also the same time s5 equal to s6, because you know this isentropic expansion, therefore entropy value, entropy is there's no entropy change in isentropic expansion, therefore s5 equal to s6, right? So so we okay with this one. So then we can move on to s6, point number 0.6, and again we have the problem where this lies, this point would lies, right? It can be either on the superheated region or it can be in the saturated region as well. So to find out that one, we have to inspect the saturated values, right? S values, SL and SG values, right? So if you look, then what we can do, we can go to the saturated tables, right? Then the pressure is 0.04 megapascal, right? Then if we go that, let me see, saturated tables, so 0.04 means 40, right? 40 kilopascal, 40, the pressure is 40 kilopascal, and the SF fluid is 1.02 and SG is 7.66, right? So 7.66. So if we come back, So the SG gas is 7.66, but the value we are getting is 6 equal to 7.57. Therefore, we can clearly determine that the S5 or the S6 or the S6 is lesser than the this value, right? Therefore, 0.6 should be in the saturated region, right? Therefore, the 0.6 is in saturated region. Therefore, we can calculate the fraction. Fraction means what is the amount of quality of the steam, or this fraction, right? This fraction, we can calculate this fraction using the S values, right? Again, we can extract the SL and SG values, right, from the table. Now this is the SL value, right, and SG value, and this is the value that we have obtained for S6, point number 6, right? So where these two came from the saturated table, right? 40. So this is the SL value, this is SL value, and this is G value, right? So our value is in between this one. That means it is in the saturated region, right? Again, we can calculate the fraction, right? So the fraction can be calculated like this. So the fraction is get as 0.985. Okay. Then we can use this fraction to calculate this S6 value, right? Enthalpy at point. So enthalpy at 100% liquid plus the difference into the fraction, right? So where this value get again from the table, right? So this is the right. So this is the 40, and this is the value, HF value, and the difference, right? HG minus SL, right? Fraction into HG minus HL, right? That is what is given in here, right? So with that we can calculate the H6 value, right? Enthalpy at 0.6 as 2601.32, right? So so far we have calculated 3, 4, 5 and 6. What remain is 1 and 2. So 1 again we can easily extract from the saturated table, because it in saturated line 100%. We have 100% liquid here. Therefore, you can simply calculate, simply extract that value from the saturated table. So if we go back to saturated table, 40, and this is the H1 value 317.62, right? HF value 317.62, right? So that is what is given here from table. H1 equal to this amount, and the problem is finding the calculate the H2 value. So it is a pump action. Therefore, we can derive H2 minus H1 in equal to minus V delta P. Why it is minus? Because we are work in is here. Work in is minus, right? Work out is plus. Work in is minus. Therefore, we have the minus sign in here. Therefore, we can formulate again H2 equal to H1 minus V delta P. So V delta P, V is a specific volume, so we can extract that one again from the table, saturated table. H1 we know, H1 317.62 plus V minus delta P. Delta P means the pressure difference. So we have the pressure difference. We have 8 megapascal. Then 0.04 megapascal. That means if we convert it into kilopascal, we have 8000 minus 40, right? Because these values are given in kilojoules per kilogram, and therefore we have to calculate this one in the kilojoule as well, right? So therefore the V value, if we look on the table, so this is the V value 40, saturated liquid V, right? Specific volume is equal to 0.001026, right? This is the value, and if we put that value here, if we calculated it, we get the H2 equals to 325.786. so up to now we have calculated all the enthalpy values H1 to H6, right? Therefore we can easily find the W net, right? So we have a small mistake here. H4 value, as we calculate in the previous, H4 value should be 2811.8 instead of 2768. So if we look on this 27, so this value should be changed, right? So you can change this value. So I have done a mistake, that's why it is there. So this value should be 2811, right? 2811 point something, 2811.8, right? 2811.8. Then you can substitute for W net, right? Then you can get a value here, right? Again same thing. Again this value need to be changed, 2811.8, right? This value. Again you can find the Q in as well. Then the neta you can derive W net divided by Q in, then you will get a different value here. Now this value should be changed because we have done so I have done a mistake here, therefore this value should be changed, right? So let's assume these values are correct, right? You get the idea, you know the calculation, therefore you can correct this one. And for the moment, for the rest of the things, we will get these values are correct. Let's assume this is the correct one, then we'll move on to the next sections, right? So this is the neta value, right? So we have calculated for the efficiency. Then the part B, we look on to the part B. Part B is the mass flow rate of steam in kilogram per hour, right? Kilogram per hour. Then now we know that from if this value is correct, right, the workout, the W net is 1615.62 kilojoule per kilogram. That means per kilogram of steam, right, per kilogram of steam it will produce, the power plant will produce 1615.2 of kilojoule of power, right, kilojoule of energy, right? Then to calculate the mass flow rate, so we know it is given that the power output is 100 megawatt. So we can divide the 100 megawatt with 10 into 6, 100 times 10 into 6 divided by 1615.2 into 10 into 3. So this is the mass flow rate. Now you get the mass flow rate in this way. You get mass flow rate kilograms per second, right? So 61.911 kilograms per second mass flow rate. So you can convert that one into hourly as well by multiplying 3600, right? So that is it. And so that is the part B. Then the part C is asking, let's part C, the rate of heat transfer Q from the condensing steam as it passes through the throughout the condenser in megawatt, right? So Q that out from the condenser, right? So if we look on the condenser, right, where the condenser, right, if we go back, so condenser start from 6 to 1, right, 6 to 1. So therefore we can calculate H6 minus H1 is the Q out in the condenser, right? H6 minus H1, right? Then so we can substitute for that one, right? So H6 minus H1 is the energy transferred in the condenser per kilogram, right? So therefore we know the flow rate. Since we know the flow rate, we can multiply that one in the flow rate as well. Then we can get something like this, right? 141.38 megawatt. Now this value should change because I have done a mistake. You will not get the same values, but somewhere close values, right? So now you can see it produce. Now this should be correct, right? Also you can check whether your values are correct, because you know most of the in any thermal system, most of the energy will be wasted, right? Now we get 141.38 megawatt, 38 megawatt of power, megawatt of energy will be wasted in the condenser, right? That is okay, right? Because the workout is 100 megawatt, workout is 100 megawatt, and efficiency is less than the 50%, right? And also we get Q rejected, Q out as 141.3. So this value seems to be correct, right? Right. So there's another part in the question, right? Discuss the effect of reheat on the Weber power cycle. So how we discuss the thing? So what basically reheat do is it increase the efficiency, because you have two set of workout. Now this is the first set of workout, right? Again we have another set of workout, right? Therefore we can, using the same setup, we can increase the efficiency by increasing the amount of work that we are getting from the system, right? Therefore reheating basically improves the efficiency, give lot more work out, can get work out from the turbine, and therefore it gives you improved efficiency values, right? So I hope this you can follow this tutorial, right? So if you have any question, we can arrange a separate session, maybe online session, to discuss the things, right? So okay, right, then thank you.